everybody, we are Group 1, Greenhouse Environmental Analyzer of Blue to Red Light, Humidity, Temperature, and CO2, or GEA. Here is GEA. Her housing is made of PETG, which is high durability and is highly resistant to heat and moisture, which are found in a greenhouse environment. On the top here, we have 3 photodiode sensors and 1 CO2 temperature and humidity sensor. Her housing holds the PCV sensor, and the lenses are held by 3D printed holders.
Here we got our white light sensor, our red light sensor, and our blue light sensor. They each have a fisheye lens. For these 2 sensors, the filters are actually baked in. I put them in between the lenses so we didn't have that much movement, and so it was a lot easier to calibrate without me having to hold the filters above or below.
The main PCB, the highlighted component is the microcontroller ESP32. This is the battery holder and the main source of power of this, the battery. This little chip is the USB to UART to program the microcontroller. This is the I2C splitter that we need in order to communicate with all the sensors, since all of them has the same I2C address and we only want one I2C bus. The component that I highlighted now is the USB port and the switch that is in order to select the battery mode or the programming mode. Then we go to back to the PCB. In the left side, we can see the red light sensor, then the blue light sensor, then the one connected with the cable is the light sensor. And in the middle of the PCB, we can see the CO2 and humidity sensor. We use a cable for the light sensor, for the general light sensor for troubleshooting featuring.
Here's our second PCB that has 10 red LEDs and 10 blue LEDs. This represents our greenhouse lighting and changes with the app. With the app, we can turn this on and off, and it affects our sensor readings for each individual plant and what ratio to red to blue light that it needs.
Here is our second PCB. So this PCB is more than an iteration of the first one, but instead of having the sensor, we have the LEDs that we're gonna control through the app, so we can control the red and blue radio through the plant.
This is our mobile app. Right now we are in the login page, but we also have a forget password. Once you get in here, you're gonna be able to put your email, and we're gonna send an email in order for you to reset your password. We also have a sign up page where you create an account with us, and then we will send you an email for you to confirm it and then be able to log in our page. Once you log in, you're going to be sent to a home page. In the home page, we have multiple options, and the first option is an analyzer of blue to red light. When you get in here, you're going to see all the data that's being collected from our log sensor from our PCB. And if we refresh the data, we're going to get different data. Same with temperature readings. When we get in here, we're gonna see the CO2 readings, temperature, and humidity. We also are able to change it to Fahrenheit in case you prefer it that way. We also, if we collect the data again, we're gonna see different readings. Now we go to LED controller. The LED controller has presets, and we also are gonna be able to manage it as we want it. So in case I want to turn one from here, another from here, another from here, and here, so the LED is going to turn on the PCB. We also have the preset as I mentioned before, 50-50, 730, all on and all off. And now we go to the threshold adjustments. When we go in here, we're going to be able to set up thresholds for our app to send us notifications. So if we want the app to send a notification whenever the temperature is higher than, let's say, 5 Celsius, we're going to be able to get notifications in real time. We're going to fetch the data, and as you can see, we get notifications. Now we also go to our profile page, where you're going to be able to update your username, name, and also you're going to be able to delete your account. And we also have different areas where you can access all the pages.
So we're gonna show one of our engineering specifications that the app can read data in less than 40 seconds. So now we're gonna turn on the light and we're gonna see how it goes down in less than 20 seconds. I should press refresh. Yeah, it went bar.
Here's our testing setup. As you can see, we have our device in there along with an independent lux meter that we are going to use to validate our readings. This outside portion is used to represent the greenhouse, and then we also have our LED panel on the top, as you can see there. So for our first test, we have the windows of the room we are in open for optimal light. So as we can see from our app over here, the reading is about 584 from our sensor. And then from the independent sensor, it is about 500.
Went down.
We completed 2 more tests at this light level and used the percent error formula to understand our data. We use this formula because we are comparing our measured value to a known true value, which we take to be our lux meter reading. Our engineering specification was to have our error be under 10%. As we can see, 2 of our tests achieved this, but 1 did not. We believe this to be an outlier, and it is what causes our mean to be slightly over 10%. Now we close the curtains and dim the lights a little bit in the room, and now we can see that our white light sensor is reading about 158, and the sensor, the independent sensor is reading about 130. At this lower light level, we see a worse output. Although our app readings are closer than what they were for the regular light tests, the percent error formula at low numbers is more variable than it is at higher numbers. We still chose to use this formula as a basis for our specification because in a greenhouse setting, we will be dealing with high lux numbers, such as over 10,000 lux. We will now do testing with higher light levels to simulate this as accurately as we can. Next, we wanted to test with even more sunlight, so we put our device on the windowsill. And we can see that for the white light, we are reading 4078, and from our independent sensor, we are reading 3744. At higher light levels, our readings have less of a percentage error due to the nature of the formula. Since these higher light levels, such as those that would be in a greenhouse, are what we are aiming to measure, we included a clause on our specification that says our error will be within 10% only above a certain lux threshold. Therefore, as we can see from this table, our specification has been met for our white light sensor. For our next test, we are going to turn the red LEDs on and then see how our photodiode reacts to that, and then turn the blue LEDs on and see how our photodiodes react to that. So right now we are going to start with the red. We can see that without any of the LEDs on, we are measuring 2 lux. If we go and turn all the red LEDs on, we can go back to the readings and see that it is now 7. Now we are going to do the same for the blue. Gonna turn off the red and on the blue. And we can see that our blue shoots up to 79 lux.
Alright, so this is our blue filter, this is our red filter. As you saw in the video, the red filter picked up a lot less lux than the blue filter. That's mainly because we're double layering the red. That was mainly just because in our test, the blue still got through the red a little bit. And so to get to match the blue where none of the red got through, we had to double it up. There would be more calibration needed to make sure that the amount of lux being read by the meter will be accurate. Right now we haven't multiplied by a value to take the transmission into account. We're only taking, comparing it to our bot sensor, so our handheld sensor over there. But right now the measurements match up with that. So that will be changed later on. For the moment, we just want to make sure that these matched up with that before we took the transmission into account.
We are now putting our device on the windowsill and looking at the red light. You can see on our independent sensor, we put that doubled up filter. And we can see that our blue shoots up to 79 lux. we are reading about 46 for our sensor, and the independent sensor is reading about 43. Now we put the blue filter over our independent sensor, and as we can see, our blue is reading about 43 lux, and then the sensor is reading about 88. Our red lux measurement has a high accuracy, as you can see from the table, with an average of 7.46% error. However, we learned from this demo that our blue sensors have to be calibrated much more. A 50% error is extreme, and it will be the focus of our work in the near future.
The big thing is, so the red was very well calibrated. As you saw, we definitely calibrate the blue a little better. It's just the different lighting conditions. You have to take different things into account. It seems in this brighter lighting condition, it wasn't as well calibrated as with the red or the white light. But that is something that we can fix. So later on, we will fix that.
We wanted to go over what we learned from this demo. That includes our successes, our failures, what we learned from our failures, and what our next steps are. Some of our successes are that our engineering specification of the app updating the measurements in less than 40 seconds has been achieved. Also, at high light levels, our engineering specification of our measured lux being accurate within 10% is a success for our white and red light measurements. Also, our app can control the LEDs individually and in preset groups, and the PCB can handle turning on all the LEDs at the same time. Additionally, our device is working with a 9-volt battery source. Our Wi-Fi intercommunication between all of our devices has been successful, and all of our sensors are working under only one I2C bus from the MCU. Moving on to our failures and things we learned from them. One of our failures was that at high light levels, our blue light measurement had a high error and did not meet our engineering specification. So we learned that our calibration still needs to be tested and perfected. Based on this, our next steps are testing and calibration of blue light measurements as well as coefficients added to take the transmission of the filters into account. Once our calibration is good, testing and coding of an automated LED system to adjust to our desired ratio will commence. We also would like to build at least 2 more prototypes in case of failure and implement a power consumption saving code. Thank you from all of us for watching our midterm demo video.